So, we're here to talk today about Kubernetes for developers. So, quick show of hands first off. How many people have any experience with Kubernetes previously? Okay, a couple. Everybody else? How about Docker? How many people have experience with Docker? A few more? Okay, good. So, my name is Jeff French. I'm the principal consultant at Moonswitch. We're a DevOps and cloud migration consultancy, and we specialize in Kubernetes. So if you need any help with that, let me know. So let's start by talking about what is Kubernetes. Kubernetes is comes from a class of product known as a container orchestrator or a container scheduler. Those terms get used a little bit interchangeably. They tend to actually mean slightly different things in that a scheduler typically is a little bit less full-featured than an orchestrator. But we'll get into what that actually means when it actually orchestrates your application. So Kubernetes is not the only player in this space. There are other schedulers and orchestrators, including Docker Swarm that you may have used, Apache Mesos /DCOS, which is kind of based on Mesos, and HashiCorp's Nomad are just a few of the other container orchestrators and schedulers that are out there. And they all do relatively the same thing, right? Or versions of the same thing. So a container orchestrator, first off, when we say container, we're typically talking about a Docker container. There are other container technologies out there that's well beyond the scope of this talk, and most of these orchestrators have the ability with some modification to schedule things other than Docker containers or Docker-compatible containers. But the job of a container orchestrator is to take a set of instructions that you give it that say, I have some set of containers that represent my application that I need to run, and I want you to run them for me, right? I don't want to be bothered with figuring out, is there room on this, I don't know, EC2 node over here, and go over there and run a Docker run command to get my container running, and then if my container crashes, having to go and say, oh, well, let me go start that container back up, or upgrade it to a new one or something like that. That's the orchestrator's job. So that's what Kubernetes really does for you. It manages a set of nodes that can run containers, and it schedules containers to run on those nodes. And it does a lot of things that are, as far as depending on how your cluster is configured, it will move workloads around to, balance them between nodes a little more or consolidate them more on nodes so that you can kind of downsize your cluster. So these are all the kind of functions of a container orchestrator and what it does. So there's two sort of sides on how you need to interact with a Kubernetes cluster. One would be the operator side, where you are typically a sysadmin or DevOps engineer who is in charge of standing up all the nodes and joining them into the cluster and making sure they stay healthy and all that. We're not covering any of that part today. Today, this is about if you are a developer who wants your apps to run on a Kubernetes cluster, this is kind of a quick start on things that you want to actually know. And we're going to scratch the surface on some things. This is a gigantic topic, and there's a ton of documentation out there on the Kubernetes website and in lots of blog posts. I'll try to kind of hint at when there's more things you might want to research on your own, but we're going to keep this at a pretty high level, intro level talk. So the first piece of vocabulary we want to talk about in Kubernetes is called a pod. Okay? So a pod is a collection of containers and volumes. So if you've worked with Docker before, you know what a container is, right? It's basically you've taken your app or some code that you've written and put it into this nice little portable container that can be run somewhere else, wherever there's a Docker engine. You've probably also dealt with volumes if you've dealt with Docker, which is essentially defining a disk that's going to be attached to that Docker container. So if you think of a Docker container as a virtual machine, because it almost is, then a volume would be like a disk that you're going to attach to that virtual machine where you can store some data and have access to a disk. So in Kubernetes, we deal with pods. And as I said, it's a collection of containers and volumes that you define. Now, typically a pod will have ideally one container. That's not always true, but you have one main container that runs your application, and that's kind of the core of a pod. is here is my web app running in this Docker container. Now, you can have multiple containers inside of a pod, depending on what you need there. One common usage is something you call an init container. So let's say that before your actual application can run, you need to actually do a little bit of pre-work before that happens. Maybe there's some secrets or configuration that's mounted in on a disk somewhere or coming in from environment variables, and you need to arrange that into like a config file that your main container is going to read. So you could have an init container that spins up first, and the way that Kubernetes handles that is it spins up your init container, it waits for it to successfully complete, and then it spins up the main container for your pod. The other interesting use for having multiple containers in a pod would be what's called a sidecar, which means that you have another container that is sort of an auxiliary container inside your pod that's doing something out of band from your main app. So one example for that might be, say, a logging container. Say your app just logs to standard out, and maybe you've got this sidecar container that's kind of sharing a process space with your main container that's scraping those logs and shipping them off to an elk stack somewhere or something like that. So that's one common use for sidecars or having multiple containers in a pod. However, you could actually have two, what you might consider primary containers in a pod. One example that I've seen referred to a lot is like, let's say you've got your main app in this main container is serving some files from a file system. So you've got a volume mounted in, it has these files on it, but these are also files that need to be updated regularly. So you might have a second container that's running inside your pod that is just in the background constantly checking some other source and syncing these files into the local volume, while your main container is still serving this web application that's serving those files. So that's another scenario where you might have multiple containers in a single pod. But typically when you think about a pod, you're generally going to be thinking about it as one main container, and that sort of represents your unit of work. So let's look at a pod spec. So Kubernetes, all interaction with Kubernetes basically is handled through a Kubernetes API, but they've got a command line tool called kube control that you can use to do most tasks against the API. And a very common method of doing that is loading what are called manifests that are typically written in YAML, but can also be written in JSON. And essentially what ends up happening here is kube control will take these YAML files, convert them to JSON, and send them to the API in order to tell your Kubernetes cluster to create certain resources. So when you're looking at Kubernetes, you're going to see a lot of YAML, and it's a really nice way to be able to express what's going on. So let's look at this pod in detail here. This is a very simple pod. It's got some metadata attached to it, namely it's got a name, so it's myapp-pod, and then it's got a label, which says, oh, this label says that the app running in here is my app. The labels are freeform. There's no actual required or standard labels in Kubernetes, although there are a lot of convention-based labels that people will apply. And you can think of labeling, if you've worked with AWS or Google Cloud or anything like that, think of it like the same way that you would as tagging, right? So if you're creating a ton of AWS resources, it's a common good practice to tag those with some consistent and convention-based tags so that you can easily kind of see what you've got running, easily issue bulk commands against those things. The same principle applies with labels in Kubernetes, right? They're a great way for you to be able to keep track of the different resources that are being deployed in order to support a given application. So then we look at the spec and the containers, and we'll see that obviously the containers here is a YAML array, so you can list multiple containers. This one just lists one, and it's called myapp-container. I define the Docker image that it uses, which is just the BusyBox Docker image, but that can be pulling a Docker image from any Docker registry where you've got your Docker hosted and that your cluster has permission to pull from. And we're defining a command for it to run, which this one is obviously just a real simple kind of echoing out hello. Now we look below that and we see that we've got volume mounts. So what I've done here is we have got a volume defined down at the bottom of this pod, and it says, hey, this is a very simple volume. It's a volume type known as a host path, which basically just takes exactly what it sounds like, a path on the host that is running this container, which is one of your Kubernetes nodes, and makes that available as a volume that you can attach to these other containers. There are a ton of different types of volumes that Kubernetes supports right out of the box, like probably 30-ish. Everything from AWS EBS disks, Google persistent disks, Ceph or GlusterFS file systems, NFS mounts, iSCSI. If there's a way to attach a disk to a VM, there's probably a way to support that in Kubernetes to get it attached to your pod and make it available as a volume. So in this, we've got a really simple, on the host at /data, we've got this directory. That directory has to already exist. There's another directory type that is directory or create, so it will create it if it doesn't exist. And then as we look back up in the container spec, we can see on the volume mounts that we've told it, hey, take that volume that we called test volume, which is a host path, and make it available inside my container at this mount path of /test-pd, right? So that means that now my Docker container, this BusyBox image, it could read files or write files to and from that mount path. You can also make volumes persistent. You can define it within Kubernetes persistent volumes, which say, hey, this volume should outlive my pod, right? I don't want this data to die when my container goes away, right? If I shut it down and spin up another container, I want to make sure that I've still got the same data there. I don't want to lose it. And so you can do that through persistent volumes and persistent volume claims, which are not included on this spec, but something else you might want to look at as you actually start looking at running real workloads on your Kubernetes cluster. Okay, great. So we've got pods, sure. So do I have to define that all the time? Well, most of the time you won't actually define a pod directly. You'll define what is known as another class of resource known as a controller. And the most common controller type that you will deal with in Kubernetes as a developer is going to be a deployment. So a deployment describes the desired state of a set of pods and manages updates to those pods. So what that means is if I want to define this pod and a set of volumes and everything, that's all fine and good, but I might need to run more than one of them, right? Maybe my app is popular and I need to run 5 web servers to handle it. Well, rather than creating 5 different pod specs with different names on my own and managing those, I can create a deployment. So with a deployment, you can actually define the number of replicas that you want to have running at any given time. And when the deployment actually starts running, what it does is it says, okay, I should have this pod running, and because you've set replicas to 3, I know I'm going to make 3 copies of it and distribute those out. And it's probably easier to explain that by looking at a definition of one. So here's the definition of a really simple deployment. So we've got, again, our metadata section where we can give names and labels, and that's all fine and good. But then the interesting part becomes this spec. So this is what's known as a pod spec, and it follows the exact same schema as the pod that we looked at previously, but it's going to be managed by the actual deployment. So under our spec, we say I've got replicas of 3, and this is to run a simple Nginx pod that's going to serve web traffic for my app. So the templates here are interesting because this metadata that's under the template over here, this is going to actually be applied to the pods. This whole template is a template for the deployment to create its own pod specs as needed based on the number of replicas that you've requested. And then we've got our same spec, and this is really simplified down to just a single container here. But we could have volumes mounted here. We could define environment variables that need to be passed in. So in the background, a deployment actually creates another Kubernetes object called a replica set. And before deployments were around, replica sets were like the recommended way for you to run a set of pods. That's no longer the case. Now, the sort of recommended guidance is not to create replica sets yourself in most cases, but instead to create a deployment, which is, again, a defined, a desired state that you want it to have. And so then the Kubernetes API is going to say, okay, cool. Because you've expressed this desired state, I'm going to make sure that I'm always keeping it in that state and doing whatever I have to do. If I see that there's only 2 of your pods running and you've requested 3 replicas, then I will spin up another set of pods to match that. So when you actually spin these up, they get distributed to whatever nodes are available, and the deployment handles that for you. And it says, okay, great. You want more of these? You can have more of them. And then the nice thing about a deployment is it becomes a way to manage your scaling as well. So if you were running 3 replicas and all of a sudden you start getting hammered with traffic, you can issue a simple kube control command to scale up this deployment to 10 replicas. And it's going to go out there and handle that for you and say, oh, okay, great. I see I've already got 3. I'll go spin up 7 more for you. Let's get those going. And we'll get into a little more detail about some of the scaling features toward the end of the presentation. So great. We've got a deployment, and this deployment is now managing all these pods that are running my app. Awesome. I need to get some traffic to that application. I need to send users there to do things typically. I mean, not always. You may have a non-interactive workload that's just doing Bitcoin mining or something. But typically, you're going to run web-based applications on a Kubernetes cluster and need to send traffic to them. Well, a service routes traffic to a set of pods. So this is basically a definition, it's called a service because it is used for service discovery, so that you can say, I need to send traffic to this pod, but I don't necessarily know the name of that pod because the deployment may have killed and created multiple pods. There may be 10 pods running, but I need to just reference it. I want to just load balance between those. So that's where a service comes in. And when you create a service, there are a few different types of services that can be created. The default type of service is called cluster IP. And what that means is that this service gets assigned an IP from the CIDR block that is internal to the cluster. A cluster IP service is not exposed outside the cluster at all. It's only accessible by other things that are running inside the cluster. Another type of service is called a node port service. So when you declare a service of type node port, you will specify a port on each one of the nodes that is going to be listening and proxying traffic for these pods. And so what it will do is if you say expose a service of type node port on port 33602, then every single node in your cluster is going to expose that port and route that traffic to your pods based on the definition of your service. And then the other common type of service that you'll see created is called load balancer. Now, what this does is it actually typically integrates with whatever cloud provider or other system you're running your Kubernetes cluster on. So let's say you're running in AWS and you create a service of type load balancer. It's actually going to go out through the AWS API and create an ELB that is going to route traffic to the nodes in your cluster. So in this case, now we're actually exposing this to something on the outside world. A node port does this as well, where you're saying, hey, these nodes, if they're accessible somewhere in your VPC, depending on how you have things configured, will actually route this traffic. Now, when you're dealing with routing traffic inside the cluster, a service actually gives you a very nice convention, if you have, which most Kubernetes clusters have, Kubernetes DNS enabled internally. So what you end up with is a DNS name like this. Whatever the name of your service is, whatever the namespace that it's running in, and then .cluster.local. So if I have, let's say, a database server running in my Kubernetes cluster, and it's maybe in the data namespace and it's called Postgres, then I could have a name of postgres.data.cluster.local. And if I want my other apps within the cluster to be able to access that, I can just feed them that name. And the service is going to take care of always routing that. Whenever new pods come up or old pods go down, the service actually handles routing the traffic to those based on a set of rules that we'll look at here in just a second. But my other applications that are consuming that get this nice, static, predictable DNS name that they can reference inside the cluster. So here is a simple service definition. So we're defining a service. Its name is my service. It's got a selector here, right? So this selector section is interesting because this actually interacts with the labels that we saw on our deployments and our pods. So what this selector is saying is that the way that I want this service to route traffic is by looking for all pods that have a label of app with a value of my app. So this is how the service is able to kind of dynamically route traffic as your pods get spun up and spun down by the scheduler. If we look at this, we're defining the ports that we actually want to route traffic to. So in this, we're just routing simple port 80 and port 443 to a target port. So this target port is going to be the port on which my actual container inside my pod is listening for these types of traffic. So I'll have my Docker container inside my pod listening for HTTP traffic on port 9376, and this service is going to listen on port 80 and direct that traffic over to the other port. Okay, so with the exception of the service type load balancer, we just said that the services don't actually expose things to the outside world by default. A cluster IP service doesn't. A node port type does, but it's very difficult to manage because it's going to be these random ports that are on 3, 5, 100, 1,000, however many nodes are in your Kubernetes cluster. So how do we get traffic from the outside world in? As we said, there is the load balancer type, which will actually create a load balancer in whatever cloud provider you happen to be running your cluster in. That can get expensive real quick. If every single thing that you, especially if you're running a microservice architecture with 30 or 40 web apps that all need to be exposed, all of a sudden you're going to be paying a lot more for those ELBs than the value they're actually providing in most cases. Well, this is where an ingress comes in. So in Kubernetes, an ingress is a resource. It's referred to as a resource even though it doesn't actually do anything. An ingress simply describes a set of hosts and paths that should be routed to a given service from outside the cluster to the service that's inside the cluster. They don't actually do anything by themselves because they actually employ what is known in Kubernetes land as the operator pattern, where there is a ingress controller or operator that you install in your cluster that actually follows these instructions that are defined in the ingress. So a really common one would be like nginx ingress, which is going to spin up an nginx instance or instances and basically read these rules and say, okay, great, you route all the traffic to me as nginx, and I will automatically dynamically configure all these backends to route traffic to within your cluster. So let's take a look at an ingress. Here is an ingress that I've used to expose a GitLab web UI in my cluster to the outside world. Now there's a few new concepts in here. An interesting one here is the annotations. Annotations are valid in the metadata of pretty much every Kubernetes object. They differ from labels a little bit in that labels have to be very simple key value pairs, whereas annotations can be more complex, as we see here with having actual URL style identifiers. Annotations are typically used to tell some other thing how it should interact with this Kubernetes resource. So in this case, some of the interesting ones here are that we're saying, okay, well, the class for this ingress is nginx. That means that I have deployed the nginx ingress controller in my cluster, and I'm saying, hey, I want this ingress to use the nginx ingress controller. There are ingress controllers that are, there's one that's specific to Google Compute if you're running in GKE. There's one called Traffic. There's, I believe there's actually an HA proxy ingress now. And you could actually run multiple of these in your cluster if you wanted to, and this annotation helps them decide which one of them should handle your ingress. Another interesting one here is this TLS Acme. I'm telling it, hey, I want you to get a TLS certificate, an SSL cert, for my ingress. In this scenario, I've deployed another controller called cert manager that knows how to interact with let's encrypt. So whenever it sees that I've created an ingress with this set to true, it says, hey, cool, I'm going to go in there and I'm going to read the data out of your ingress and I'm going to go interact with let's encrypt to automatically issue you an SSL certificate. There's a lot of really interesting things can happen there based on these annotations. The actual ingress itself is specifying that, hey, for this given host, I want you to route this path to this back end. It's a very, if you've ever configured Nginx or HA proxy, it's a very, very familiar type of concept where you're saying, hey, when you see this come in, route it over here to this back end server transparently to the user, pass along some IP data, stuff like that in the headers. This does the same thing. So I can actually have this is passing all traffic at the main route path, but I could have it say just, /users if I wanted to route that to some different service for a reason. I can also have multiple rules defined in here if I need to. And this is telling it, this back end is telling it the name of a service. So just as we saw in our previous example of the service, I'm telling it which service to route to. So you can see we've got this kind of multi-tiered thing where we're saying, okay, an ingress helps me define how traffic comes into the cluster and goes to a service. Then a service helps me define how traffic that's already gotten into the cluster gets to its ultimate destination on an actual back end. And then in the TLS section, this is just defining a little more data about where this SSL cert would be. So in this scenario, we would end up with a Kubernetes secret called GitLab TLS that would have a couple of keys in it that hold the private key and the public cert that were obtained from Let's Encrypt, and make that available to whatever ingress controller is trying to run this, such as our Nginx instance. So let's look at what all that looks like, right? So based on what we've talked about so far, we have, this is a representation of kind of what we just went through, which is that we've got traffic that's out here in the internet that arrives at some host name that we've defined via external DNS that hits our ingress. So in this case, let's say our ingress is the Nginx ingress controller. So it's hitting an Nginx instance, and that Nginx reads its own config and says, cool, because you came in on this host and path, I know that you want to go to a particular service. So it routes that traffic down to the service. Once your traffic hits the service says, okay, great. I know how to find the pods that you want to use, and I'm going to send you to one of them. And it just goes basically a round-robin DNS at that point, where the traffic now hits one of the pods that I have running in order to serve that traffic. So this is sort of the basic application setup that you'll see for most things that you deploy into Kubernetes, especially as a developer, an application developer. A lot of times we're building web UIs or APIs, and this is going to be a really common paradigm for how you actually get traffic to your application that's running inside of a Kubernetes cluster. So now that we've got our, actually, I'm tired of standing behind this podium. If I can move just a little bit without messing up the Twitch stream. So now that we've got our application running as a deployment, how do we update it, right? This is one of the reasons why you use a Kubernetes deployment instead of directly using a replic set or pods yourself, is that the deployment has a lot of options that help you manage how you actually roll out updates to this thing. So whenever I come in and say, okay, we've shipped version 1 of our app to Kubernetes as a deployment. Now, we've got version 1.0.1 ready to go because we found a bug and we've got to release it. So when I go and actually update, say, the image tag that I'm deploying for my Docker container of this deployment, Kubernetes sees that and says, okay, great. Well, now that you've made an update to this deployment, I'm going to look at your update strategy and figure out how it is that you want me to roll this out. The one option that it has is recreate. In that scenario, it just basically goes and nukes all of your pods and recreates all of them with the new definition. that's a way to go. There's probably a good use case for it. I haven't had a good use case for it yet, because typically I'm deploying apps that are actually in use. So the default is a rolling update strategy, which means it's going to, based on a set of rules, look at all the pods and say, okay, cool, I'm going to go through and upgrade them systematically until I've got them all done. And when you're doing that, you can define one of two types of strategies. There is the max unavailable, and then there is the max surge. And these aren't exactly mutually exclusive, except that if one of them is set to 0, the other one can't be. And we'll get into that just a little bit. But what we've got here is, if we do a max unavailable, then what we're saying is that a certain number of my pods can be unavailable at any given time during this update, and that's okay. And you can express that as either an absolute number of 5 pods, or you can express it as a percentage, like 25% of whatever I've got deployed. I usually find a percentage to be something that scales a little better. When you actually start scaling your deployment up and down, you probably care more about the percentage of total pods than the actual exact number. So the other type is a max surge. So a max surge defines a number of pods that can be running in excess of what you've defined for your deployment. So if I said on my deployment that I want to have 5 replicas, then a max surge says that so many pods can be above that number without the deployment starting to kill them off as, oh, hey, that's more than what you asked for. So let's look at this in a little more detail with an example. So let's say I've got on our web server Nginx replica set to 10, saying, all right, Kubernetes, I want to always have 10 pods running, serving all my web traffic. So in the scenario where we have defined a max unavailable of 3, here I've chosen an exact number, despite the fact that I just advised you with percentages, just for simplicity's sake. So in this scenario, it means that once I tell Kubernetes to update our deployment, it will say, okay, cool, well, you've asked for 10 copies of this to be running, and I've got a max unavailable of 3, so I'm going to go kill 3 of your pods and update them to this new spec. And I'm going to wait until they come online before I do any more, right? So it starts those updates, and one of them might finish before the others. So as soon as one of them finishes, then Kubernetes says, okay, cool, well, I can go take down another one of your pods that needs to be updated, right? And at any given time, it's going to make sure I still have 7 available, and at least 7 available, and no more than 3 that are not serving traffic. Now, in the max surge scenario, we go the other way. It says, okay, you've asked for there to be 10 of these pods running, and I'm not going to take it any lower than that. Instead, because you've got a max surge of 3, I'll bring up 3 new pods. And when they're ready, I'll start swapping those in to your set of 10 and swapping out your other ones. So in that scenario, we might go as high as 13 pods that are active and serving traffic. And which one you choose really kind of depends on your application and your constraints, and whether it's more important to keep more pods up and serving traffic, or if it's more important to stay under a certain number so that your cluster doesn't get overloaded. One thing to consider is that whenever any of these schedulers like Kubernetes are trying to schedule their pods, they look at a few different things to say, hey, is there enough CPU and memory on this node to put this pod there? And if there's no place to put it, then those pods just sit there and never get spun up, right? So that might be a scenario if you know that you typically run sort of at the capacity of your cluster for whatever reason, then you might want to choose a max unavailable update strategy so that it starts pulling pods out and freeing up those resources before it creates new ones. If you've got plenty of headroom on your cluster and it's more important to make sure that you've got enough, pods serving traffic, then you might want to go with a max surge where it says, okay, great, I'm going to make sure that I'm always got enough 10 pods running to serve these customers, but I'll scale it up as high as 13 in order to get these updates rolled out.
So those
Yes, so the only real exclusivity rules that apply to these, according to the documentation, and I haven't done a ton of experimenting on these two in practice to see how they actually play out in really large-scaled scenarios, but is that if max unavailable is set to 0, then max surge cannot be 0, and vice versa. If max surge is set to 0, then max unavailable cannot be set to 0, right? You have to allow it to do one or the other, or it'll just be deadlocked and can't do anything. Now, if you define both of them, again, like I said, I haven't done a ton of experimentation in this scenario, but what I expect would happen is that it's going to basically work within those limits. So in this scenario, if I had both of these things defined, then it's going to start creating pods and killing pods as it needs to, and the rule set it's evaluating it against is, okay, am I above 7 and below 13? And as long as it's in that range, it's free to start creating and killing pods all that it needs to. Okay, so there are several other ways that you can run pods in Kubernetes. We covered a deployment, which is a way of just essentially keeping things running based on some described state, right? Other things in the same family as deployment would be stateful sets and daemon sets, which are a little bit less common and a little bit more advanced. We're not going to get too deep into them here. Suffice it to say that if you have a daemon set, it's like a deployment, except it means that it's going to run, rather than a number of replicas, it's going to run that pod that you define on every single node. So it has a one-to-one relationship with the number of nodes in your cluster if you do a daemon set. That's typically used more for things like log scrapers and aggregators or things like that where you're kind of monitoring health usually, or anything else that you need running on each node exactly once. A stateful set is similar to a deployment except that it makes some guarantees around identity and ordering of your actual pods. And that's more commonly used for things like databases where maybe you've got a leader and 2 or 3 replicas, and which one is the leader and which ones are the replicas is actually very important in that scenario, and you need to make sure that there's a certain amount of availability and that things are rolled out in a certain way. And those are 2 things that you can dig into a little bit more if your workload, if you think that you need that for your workload. Typically you'll use a deployment. However, another class that you'll actually use quite a bit as a developer is a job. So it's similar to a deployment in that it describes a set of pods, except with a job, it runs it once to completion for each pod that you define. And usually it's one pod. It could be multiple. And you can do some interesting things with parallelism and queued workloads, but a really typical example for using a job would be database migrations, right? Whenever I deploy a new version of my app, I want to make sure my database is migrated to match that version. So I can create a job, and that job says, okay, great, create this pod based on this pod spec and run it until it completes and completes successfully. So what that means is if it goes and starts my job and this pod runs, but for whatever reason, let's say the database is unavailable or something else happened and it couldn't actually run the migrations and complete them successfully, that pod is going to die and it's going to get restarted again. And Kubernetes is going to keep trying to do that until it successfully completes once. Now, once you've actually run that database migration, you're like, cool, I don't want to do that anymore. So it stops. Your pod exited successfully, indicating that it was done, and it completed whatever it was trying to do. And now that's it. You're done. So that job just sits there. And it just sits there in a completed state. You can go back and inspect the state of it, and then you can delete the job if you want, and it'll clean up any pods that it had left laying around in a non-running state. So let's take a look at a job. Again, we see that the spec looks very, very familiar, albeit tiny. That we've got this essentially the same kind of template. It follows the same template as the pod spec for a deployment and other things. And the only real difference here is that because the kind is set to a job, and there's a few other things like a back off limit that can tell it how much it needs to back off from jobs, or that it should stop trying to run them if it fails 4 times, then just don't bother trying anymore. But it's very simple. very simple definition of a pod with the caveat that it's only going to run once. Now, another sort of extension in the job family is actually the cron job. So the cron job is kind of a controller type object which says, hey, based on some cron expression, just like you would expect, I want you to create jobs for me. So if I create a cron job that has a, has a cron expression that tells me to run, I don't know, once every night at 2 a.m., then once every night at 2 a.m., Kubernetes is going to try to create a job. It may not succeed in that, so there's not as firm of a guarantee on cron job execution as there would be with, say, just traditional cron on your system. But it's going to create a job and try to have that job run. And it's going to do that every night at, say, 2 a.m., which is a great way to, I don't know, back up some files or a database or something like that, or perform some sort of maintenance task. So those are jobs and cron jobs. And then, so I promised we'd get back into some of the scaling stuff, as that is one of the interesting, sort of promises of Kubernetes and the cloud, right? Is that you can scale things, to meet demand, and then you can scale them back down when you don't have demand and save some money, right? So from the developer side, one of the ways that this happens, you can obviously go in and scale a deployment yourself. If you notice a spike in traffic, you can go and issue a command that says, scale this deployment up because I need more pods. But do you want to watch the dashboard all day to find out that there was suddenly a spike at 3 a.m. and you needed to go issue that command manually? Probably not. Instead, you can use a horizontal pod autoscaler. So this will scale out a deployment based on observed CPU utilization or other metrics. And I probably should have put an asterisk after that, or other metrics, because that part gets well beyond the scope of this talk. Suffice it to say that you can actually monitor different metrics, such as the number of hits coming in on an ingress, or disk space or something like that, right? But we'll just talk about them in the simplistic form of CPU utilization. So let's say I'm running this app, and this app is starting to, that the aggregate CPU usage across all of my pods, say I've got 3 pods running, and they're averaging out and they're aggregating up to 80% or 90% CPU utilization, and I say, oh, well, we're busy, we better scale up. So if I've already defined that in a horizontal pod autoscaler, then the Kubernetes API is already watching that for me, and it says, oh, hey, we've hit the threshold, add some more pods, right? Scale it up, take it from 3 to 6, and you can set the definition on what your min and what your max is and which metric you're tracking. And the way you do that is with this kube control command. It's really hard to see, sorry. But basically it just says kube control auto scale deployment. You give it a deployment name. You tell it you're watching for CPU percentage to be above 50, and I want a minimum of 1 and a maximum of 10. So what the horizontal pod autoscaler is going to do is it will scale your pods up or down based on these observed metrics. So if we're running above 50% CPU and we need more pods, it's going to add those in. And then later, when the wave of traffic has subsided and our aggregate CPU usage is down, it's going to start scaling those pods back in as well, right? Now, this becomes really, really interesting when you deploy it with something that would be more in the operational side of a Kubernetes talk, which is a cluster autoscaler. So there are cluster autoscalers for, let's say, Google or AWS or something that will say, hey, whenever Kubernetes is trying to schedule these pods and it says, hey, I don't have anywhere to put these, right? Like all my nodes don't have enough CPU or memory to support this pod that I need to schedule, so it's just pending. Then the cluster autoscaler would see that and say, oh, well, let me add some more nodes to your cluster, through an autoscaling group or whatever else. And it goes out and puts more nodes in the cluster, and then all of a sudden the scheduler can now find a home for those pods. And then the cluster autoscaler does the same thing in that periodically it says, hey, well, we've got more capacity than we need. Let's consolidate some of these pods onto a couple of nodes and take a node out. Using this, you can finally kind of realize the true elasticity of today's modern cloud environments, where based on observed metrics that your application cares about, you can now dynamically scale up, to as big as you really feel is necessary or need without human interaction. Just let the machines watch the traffic, take the action based on rules, scale it up. Now you're handling enough traffic, and then when everything dies down, all of a sudden it scales back in, so you're not paying for all that capacity you don't need. So once you get into horizontal pod autoscalers and cluster autoscalers, you really get the true kind of promise of why people want to use things like the cloud and Kubernetes in order to actually run their workloads. All right. Question and answer time. If you've got questions, I'll try to give them answers. And yes?
So when the service goes to schedule work on a pod, you mentioned it round robin based, does it look at the load before it tries to do that? Is there a way to do that?
Whoops. Oh, yeah. So the question is, does it, when a service goes to route traffic to a pod, does it look at the load on that pod? By default, no. I think I saw an option, or it may have been some sort of an add-on that could do that, but by default it just does simple round robining. Although I believe you can configure sticky sessions, so that could come into play as if it knows that a particular pod is not is overloaded with concurrent sessions.
I got one more real quick.
Okay.
On the rolling update, does it wean traffic before it pulls pods offline?
So the question was, does the when you go to execute a rolling update, does it also take traffic away before it does that? So yes and no, right? In that it's going to go kill a pod, which means that pod is going to immediately be marked before it even gets killed. It kind of, this all happens like that, but it's going to actually mark the pod as unavailable, which means that the services that try to route traffic to it say, I only route traffic to available pods. So they're constantly, every time they need to route traffic, they're saying, all right, well, where's the list of available pods? That one's not in it, so I won't route any new traffic there. Now, if you have a sticky session that was routed there, I don't actually know what happens with that. But that's essentially how that works. And so while it's not explicitly making decisions like, oh, I should take away traffic for this, it's sort of this composition of all these other rules that we talked about that dictate how that traffic's going to flow.
Okay, so it pulls it out of the pool, so no new stuff goes to it.
Right.
But if it's in the middle of trying to service a request, it's potentially that it could kill, basically it could kill the pod in the middle of trying to service a request. It's not going to wait for connections to be weaned off or anything like that. It's just going to take out availability and kill it.
Right. So to clarify, yes, he was saying that it's not going to necessarily wait for all connections to be drained off of a pod before it stops sending traffic there. Yeah. So and again, this really this comes down to a term that has been getting thrown around a lot lately about cloud native and designing cloud native applications, and that really becomes part of it, right? Like in a cloud native application, you should be prepared to handle that scenario for your customer where, at any given time, the thing running my application code could get cut off, and I need to make sure that my client on the other end has some kind of retry, or that it's okay that connection be dropped, right? And that's going to be very, very application and even particular endpoint or request dependent to figure out. But it's something that you should be thinking about as a developer who's designing applications to run on these cloud native systems. Yep. Another question? Yes.
Availability when you're upgrading Kubernetes, how does that work?
I'm sorry?
Availability when you're, like, say you have to upgrade Kubernetes, how do you stay highly available with your apps?
Okay, so yeah, the question was, how do you stay highly available with your apps when you have to upgrade Kubernetes itself? This gets a little more onto the operational side of this, but essentially because Kubernetes is filled with nodes and node pools, what you would do is you would simply add more nodes, and then that are running the newer version of Kubernetes and the kubelet API, and your other nodes that have apps on them, there's a few series of commands that you can run. You can cordon a node, which basically says, hey, don't schedule any new work on here, but leave the work that's already there running. And then you can also drain a node, which tells Kubernetes to start taking work off of that node and finding another place to schedule it. So typically your path there would be add some new nodes, cordon and drain your old nodes, and at whatever pace makes sense for your application. And so that Kubernetes will then start taking those pods off and putting them onto the new nodes, and they can't reschedule onto the old nodes because you've already cordoned them. So. All right. Any more questions? No? All right. Well, thank you very much. Again, I am Jeff French with MoonSwitch. If you need help with DevOps, continuous integration, Kubernetes, cloud migration, moonswitch.com. Get in touch. We'd love to help you out. And I have a few T-shirts and stickers here to give away. So if anybody wants a T-shirt or sticker, let's see here. I've got a size XL T-shirt. Any takers? All right. Oh, sorry. I've got a size large T-shirt. Yeah, go to this side of the room. Make sure this is the large. All right. And then I think that leaves me with a medium. Anybody take a medium? There you go. Very excited for the medium. Also, I'll have some stickers just sitting up here. If anybody wants them, come on by, grab a sticker, decorate your laptop. All right. And that's all we've got for today. Thanks very much.